Problem set number 11, double integrals part 1. We'll have several different parts to this problem set. In this section, we're going to use a double integral to find area and also average value. If we have this rectangular area, we'll start with rectangles to keep things simple. We could break this up into a grid. This little rectangle here is of dimensions dx and dy. Dx is a horizontal change, dy is a small vertical change. And if you multiply dx times dy, it gives you what we call a dA, a small element of area. We can use a double integral. In this case, we have, these are really x coordinates on the outside. And then in here, inside, we have y coordinates. You can kind of match these up, dx on the outside, dy on the inside. This just says x goes from A to B, so we're summing along this horizontal axis, and for each x, that's like a double nested loop in computer science, for each x, y is going to go from C to D. So we're starting here, we're summing along here, we go from bottom to top, bottom to top, bottom to top, bottom to top. We add up all the little infinitesimally small rectangles, and guess what? It adds up to the area. This is pretty predictable what happens. The area in this case is simply B minus A times D minus C. It's just length times width. Of course, we can expand this. This could be any shape region. Next problem set, we'll talk about other regions that are not rectangles, but we have to start somewhere. We'll talk about average value in a minute. So, for instance, look at this example. Suppose we want to use a double integral to find the area of this rectangle, 2, 3 cross 3, 5. It's a Cartesian product. X goes from 2 to 3. Y goes from 3 to 5. You can sketch a very simple rectangle. There's 3, there's 5, there's 2, there's 3. It's this rectangle right here. And we can put our X and Y there. And then we can set up a double integral dy dx. First of all, start on the outside. X goes from 2 to 3. And then for each x, y goes from 3 to 5. Now let's talk about evaluating this double integral. We start on the inside. And this is really an anti-partial derivative. There's nothing to integrate here yet, so we're not so worried about that. But integral of dy is just y. And so we have integral from 2 to 3, y from 3 to 5, dx. And then that's going to be integral from 2 to 3, plug in 5, plug in 3, dx. Of course, that's 2. Then we take an antiderivative of 2 dx, which is 2x from 2 to 3. And we get 2 times 3 minus 2. And guess what? That's 2 times 1 or 2. We just evaluated our first double integral. It's no more complicated than that. And next we're going to move on to average value. Suppose we have some function f of x, y that's defined on this region. And we'll go through an example in a minute. We can find the average value by integrating the function dy dx. This is really, we're taking a weighted average of this function, where the function value is going to be weighted according to this little element of area, and then we divide by the total area, b minus a times d minus c. This is an irregular shape. We'll see this area gets replaced by a double integral itself. We can place a double integral down here, but of course it's just as easy to just multiply length times width. And let me give you a simple example. let's suppose we want to find the average value of f of x, y equals 3y on the Cartesian product 0, 2 cross 0, 4. And just to draw you a little picture here, 0, 2 on the x-axis, 0 to 4 on the y-axis. And of course we have our rectangle. Now 3y, that's a linear function along the y-axis. Right here, 3 times 4 is 12. Halfway in between it's 6. And then down here it's 0, right in the x-axis. If you can take a wild guess what the average value is, it's going to be 6. If it's linear, you can do that. It's halfway between the max and the min. If this were a quadratic, like 3y squared, not so easy. So we should get 6. What we're going to do is integrate the function, and you'll see your first example of a double integral where you have a function in here. Then we're going to just simply divide by the area. So let's go ahead and integrate. X goes from 0 to 2. Y goes from 0 to 4. And we're going to integrate 3y dy dx. And the order doesn't have to be done this way, by the way. You can switch this around, but you have to switch these limits. If you put y on the outside, then we go from 0 to 4 on the outside and 0 to 2 on the inside. If this is anything other than a rectangle, it's not so easy. You can't just switch them. And we'll talk about that later, a couple of sections from now. It's a little more complicated. Okay, now we integrate on the inside. And we're going to integrate 3y dy. It's just an anti-partial derivative. There's no x here, so it's just a normal integral, actually. You get 3y squared over 2, integral 0 to 2, 3y squared over 2, and that's from 0 to 4 dx. And then we can plug in 4, plug in 0, integral 0 to 2. You plug in 4, 16 over 2 is 8, times 3 is 24 dx. 24 minus 0, but that's 24x from 0 to 2. And that gives you 48. Okay, and that's just the numerator. We haven't found the average yet. So F average is 48 divided by length times width. You can plug in the subtraction, or you can just length times width is just 2 times 4. 48 over 8, which is 6, as I predicted. That's the average value. It's no more complicated than that. Let's look at one more example that's a little bit more difficult. Let's suppose we had 3x and y plus x on the same interval. It's good practice because these anti-partial derivatives can take a little reflection. So we are going to do a double integral first of all, 0 to 0 to 4 and you can put this alphabetically in order if you wish. First integral, now you have to integrate x dy and 3y dy. And keep in mind, I said this is an anti-partial derivative. You're treating x like a constant. So a lot of examples in physics where you do an integral like this, and it turns out x is not constant. You have to write x as a function of y possibly. But in this case, it is constant. When we do the integration, we're integrating from y lower to y upper, x is fixed. And that's why you see the x coordinate stays the same. Conceptually move over a little bit, x stays the same. That's why you can treat this x as a constant. And so we have integral from 0 to 2. Now it's x dy gives us xy. 3y gives us 3y squared over 2. And that's from 0 to 4 dx. Now we have to plug in 4 for y. X stays as a variable. You can plug in 0, but that's just 0. So plug in a 4. This 4 gets plugged in right there and right there. So you get 4x plus 16 over 2 is 8 times 3 is 24 dx. And this gives you 4x squared over 2 plus 24x. And that's from 0 to 2. Okay, that's really 2x squared. You can simplify it. 2x squared, plug in 2, you get 4 times 2 is 8 plus 24 times 2. And that's all together 48 and 8, 56. Now in this case, F average is going to be 56 over still the same area. Area is simply 2 times 4. So 56 over 8, which is 7. Okay. Okay, that's all for this video. We'll be back. We're going to talk about mass, third topic.